after we did 2 experiments, now we feel we are ready to get a final conclusion. So we need to get a number of multiplication reduction for the general case n, degree n polynomial. Yeah, that's the last round data processing. Yeah, so we're doing data processing. Yeah, this is last round. Yeah, all right. Now here, yeah, so we already. Yeah, so here in our last round, I want to introduce some new concept here. Yeah. So if we look at our 2 experiments for n equals 2 and n equals 3, so you can see we apply certain method as much as possible. So here I use the general wording. The certain method here refers to the factorization method. Factorization method, yeah. So let me just use, this word here. That's what I'm talking about here, factorization method. And this approach applies certain method as much as possible. There is a name in algorithm context. It's called a greedy algorithm. Greedy algorithm, a special type of algorithm. People call it the greedy algorithm. Yeah. In the next slide, I will explain a little more about this greedy algorithm. Yeah. All right. Then the idea in our last round data processing, the idea, we want to push this method to the general case, degree n case. Yeah. All right. Yeah. So here the strategy for the degree n case, we want to do the generalization of our factorization method. Yeah. And when we do the factorization, we take this approach, do factorization as much as we can. Here, the phrase as much as we can, we actually apply the greedy idea, the greedy strategy in the greedy algorithm. Yeah. All right, so what's the greedy algorithm? We apply some property as much as we can at each step. That's the meaning of the greedy algorithms. We apply some property. In this example, we apply factorization property as much as we can at each step. That's the greedy strategy, greedy algorithm. Okay, all right. So here we do this step at each step. We do the greedy strategy at each step. What do you mean each step? Each step means local operation. So it's a local operation. One step. So when you take the greedy strategy, you just look at the current step. You apply the factorization method. You only look at the current step. You do not look at previous step, next step. Only the current step. So it's a local operation. So it's not a global operation. Okay? Yeah, so that's a typical property of the greedy algorithms. Yeah. So then the conclusion of applying the greedy algorithms. So a greedy algorithm is locally optimal. Yeah. So when you look at one particular step, your strategy is optimal. Yeah. Because you do the best you can. That means optimal, But that optimality is local optimality, not global optimality. Okay? The global optimality, that means you need to consider all the steps globally. Yeah. Here, local optimality does not guarantee global optimality. Okay? Yeah. Although each step, your decision is optimal at each step. But if you consider multiple steps, then your decision may not be the best, optimal. Okay? Yeah, so that's the main property of the greedy algorithms. Yeah. All right. Yeah. Yeah. And people may ask this question. Yeah. Why you do not take the strategy with global optimality, not local optimality? Yeah, the answer is simple. Because too hard to get a global optimality. Okay? It's very easy to get a local optimality, but extremely hard to get a global optimality. Yeah. So people just cannot do it. People cannot find easy way to have the global optimality. Yeah. Too hard. Yeah. So that's the reason people take the simple way, only ensure the local optimality. Yeah. All right. So it may not be optimal. Yeah. Because when we say an algorithm is optimal, it must be global optimal, globally optimal. If it's not globally optimal, then we do not say this algorithm is optimal. Okay. Yeah. So it may not be. So the greedy algorithm, if you look at the solution globally, it may not be optimal. Because it could be very hard to get a globally optimal solution. Yeah. Very hard to get it. Yeah. Yeah. So that's the understanding. That's the basic understanding of the greedy algorithms. Yeah. All right. So now, after I explain this important, this simple but important greedy algorithms, later we have a few more chances to apply the greedy algorithm. Yeah. All right. So now let's apply this greedy strategy when we generalize our factorization idea to the general case, degree n case. Yeah. So when we start, we have this general formula expression. Yeah. So with the pattern, so now we use the, our degree 3 factorization example as the guidance to guide us to get the formula for the degree n case. Yeah. All right. So we want to do the factorization as much as we can. That means we will do many rounds of factorization. The first round, you get this first pair of parentheses. After that, you get another round of factorization, so another pair of parentheses, and keep doing it until you get the last round of factorization, so the last pair of parentheses. Okay? Yeah. 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 So that's the result of this greedy strategy. Yeah. So each round we try to use the, factorization to cover as many terms as possible. That's our greedy strategy. Yeah. So each step, we try to do the factorization on the number of terms as much as we can. So at the end, we get this formula. Okay, all right. So now let me ask you the last question for this problem. How many multiplications do we have with this final version of formula? Can you count the number of multiplications based on the factorization form you see here? 10, yeah, correct. 10, yeah, n multiplications. That's correct. Okay, that's correct. Yeah. So here, how to get this n? How to get this n? Here I like to practice the counting technique I mentioned before, counting by reference, another time. All right. The first pair of parentheses, because the first multiplication corresponds to the first pair of parentheses corresponds to the subscript 1 of A1. The second multiplication from the second pair of parentheses corresponds to the second subscript 2 in A2 coefficient, and so on. The last multiplication corresponds to the subscript of the coefficient an. Yeah, so it's a one-to-one correspondence, right? One-to-one correspondence. So then, in order to count the number of multiplication, we just count the number of subscripts these multiplications are corresponding to. Okay, so 1, 2, these are the subscripts that all the multiplications are corresponding to. That's n. Yeah. So the counting by reference technique can also be used here. Yeah. Then you can see after this final round of factorization and the counting, yeah, we get this method is called Horner's rule. Horner's rule method. Yeah. Yeah. All right. All right. Yeah. So we have this. Yeah. Next, we want to see how big is the improvement, right? We know it's a good improvement. It's a good improvement. Yeah. But how good it is, how good this improvement, we do not have an idea, right? Yeah. So our last topic, V.4, we want to visualize the performance improvement. We want to feel about it. Yeah. How big is the improvement? Yeah. All right. So let's, here I try to find a way to impress you. How big is the improvement? So here we see the difference on the multiplication reduction in these two formulas. Before we apply the factorization technique, we get this many multiplications. Then after we apply the factorization technique, then we have this many multiplications. And here, two different formulas. Okay? Two different formulas on paper, so you may not get a good understanding on the difference. How big is the difference? Can you get some feel about it? How big is the difference? How big is the difference? Yeah. So here we need to get some concrete feel about it, about the difference. Yeah. Yeah. So here the impact of multiplication reduction. We want to feel it. We want to view the big difference. Yeah. So it is too abstract to feel about the difference. It is better to try out a couple of concrete examples. Let's do 2 experiments to see, we want to use concrete numbers to see how big is the difference between these 2 methods. Brute force method and the Horner's rule method. These 2. How big is the difference? Yeah. All right. The first experiment, let's look at n equals 1,000. Yeah. So this time we use a relatively large number, 1,000. When n is 1,000, let's compare the values of these 2 formulas. Yeah. The Horner's rule, this time we need 1,000 multiplications. The brute force method, based on the formula here, I use approximation. When we plug in, 500, guess 1,000 times 1/2, 500, 500 from 1/2 of the n, then parenthesis 1,001, I just take 1,000, approximately 1,000, then we get this approximation number, okay? 500,000 approximation number. Yeah. The difference is relatively small, so we do not need to write exact number. All right. Now you can see the ratio is 500 to 1 ratio. That's quite big, right? Yeah, that's quite big. The Horner's rule method only used execution time that is 1/500th of the response time used by the brute force method. 1/100th. Yeah. 1/100th. That's about 0.2%, right? Approximately 0.2%. Okay? If we use the execution time, that's quite big. Okay? All right. Then I like to another experiment to impress you more. Yeah. All right. So this time I take n equals 1 million. 1 million degree polynomial. Yeah. 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 So here we assume in the real world situation, sometimes we may need to evaluate a polynomial as big as 1 million, this big number. Okay? When n equals 1 million, let's compare the values of these 2 formulas. Horner's rule, we get 1 million multiplications, but now let's plug in 1 million in the brute force formula. How large is this number? Here we still use approximation. How large is this number? Okay, 500 billion, right? 500 billion. This big. Then we take the ratio. The ratio between these 2 numbers, that is 500,000 to 1 ratio. 500,000 to 1 ratio. Is that huge difference? Think about huge difference. Yeah. How big is this ratio? 500,000 to 1. Yeah. Yeah. Here I want to use another way to give you feel about the big difference of this big ratio. Yeah. All right. Suppose we apply these two methods on a particular polynomial, and we know the difference of their response times this big, 500,000 to 1 ratio. In order to see the difference better, so here I use the concrete time unit here. For the Horner's rule, this one corresponds to 1 second. Suppose if we apply Horner's rule on a degree, 1 million degree polynomial, we just need 1 second to complete the evaluation. So that's the Horner's rule part. If we evaluate the same polynomial using the brute force method, this time you need 500,000 times of that amount of time, so that's 1 second. So you need 500,000 seconds, right? That's the ratio, 500,000 to 1 ratio. So to evaluate the same formula, the Horner's rule, you only need 1 second. If you apply the brute force method on the same polynomial, you need 500,000 seconds. How large, how much time is this 500,000 seconds? I convert it to number of days, 5.8 days. 5.8 days, that long. That long. Is that difference very big? 5.8 days versus 1 second. That's the difference. You evaluate the same polynomial. The good algorithm, you only need 1 second. So after you hit the enter, you see the result after 1 second. All right? But if you apply the brute force method, after you hit the enter, you need to wait 5.8 days before you can see the answer. Before you can see the answer. That's the huge difference. Yeah, think about that. Yeah. So from this example, I want to make a point. The good algorithm and the bad algorithm, the difference is huge. The difference is huge. And we want to choose the best algorithm we can find. To solve the same problem, we want to find the best possible algorithm. Yeah. So this example tells you how big is the difference. And in our first programming project, we will compare these two algorithms. Yeah. So I will post a project description this weekend. Okay? Yeah. All right. Yeah. So we finished this topic. Any question about this topic, part B? Yeah. Polynomial evaluation. Yeah. Yeah. Try your best to understand the details. Yeah. All right. So if no question, then I want to move to part C. Yeah. Part C. New topic. Yeah. All right. So let me get out. Yeah. Yeah. Part, yeah, here. Yeah. Then bring up part C and D. So today we can only, before the end of the class, yeah, so we can only do one problem here. Yeah. Yeah, hopefully we can, yeah, because our part C, let me see. Our part C, yeah. 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 first two topics. Let's try to do the first two topics of Part C today. Yeah. All right. Part C, role of data structures in algorithm. C.1, search unordered arrays. So let's solve our computing problem number 2, search an unordered array. Given an unordered array, so we use this notation, array capital A with indices from 0 through n-1. It's a total n elements. And a search key, capital K. We want to find an index I such that K equals capital A of I. That's the standard search question. Yeah. So the problem type, this one, it's the search type. Yeah. And the data structure we use here, array. Yeah. Simple array here. And the reference section 2.1 on page 47. Yeah. All right. Question: why the data structures are important in algorithm design? Yeah. Yeah. So the answer is pretty simple. Yeah. Through data structures, we can make our data well organized. Yeah. Remember the last time in our first lecture, I addressed the point, the importance of well-organized data. So we count the number of squares on a chessboard. Yeah. So we organize our data first. Yeah. So you know, the data arrangement, to organize your data in a certain way, is very important. Yeah. So usually we use data structure to do that. Yeah. All right. So find the required data faster. If you organize your data well, so you can find the required data faster. Yeah. Yeah. And in this way, we can get a better performance. Yeah. In our next module, module 2, I will show you another example addressing this point. Yeah. So here in this example, actually we do not see this point explained in a lot of details. Yeah. So to see this point better, we need to use another example in module 2 to see it better. Yeah. All right. Analysis. Yeah. The basic operation we used in this example, comparison. Okay. So here we do not do addition, we do not do multiplication. Here we need to do comparison. It's a search problem. So our main operation, comparison operation. Yeah. So we need to compare the given key, capital K, and any element in the array, A of I. Yeah. And see if K equals A of I or not. Yeah. So at the beginning, we start our comparison from the first element, I equals 0. So we only have two possibilities. The first one, K equals A of I, and the second one, not equal. So not equal, greater or less, so we do not want to tell the difference, greater or less. So we treat them the same, unequal. unequal case. Yeah. All right. So for the equal case, the search function returns index value I. Yeah. So for the unequal case, we need to do further iterations. Yeah. So next iteration, we compare capital K and A of next element, A of I plus 1. Okay, so we need to consider two possibilities again. Yeah, but at the end, we need to do the comparison between K and the last element. Last element with the, index value n minus 1. Yeah. Okay, all right. If K is still not equal to the last element, then we return -1. Yeah. Because -1 is not a valid index, right? It's not a valid index. So when you see the search function returns a negative value, you know the meaning, the special meaning. It means the key cannot be found in the given array. Yeah. All right. So that's the typical way people do the, the simple search here. Yeah. All right. So the algorithm I put here, it's called a sequential search or linear search. Yeah. Yeah. Sometimes people call sequential search. Sometimes people call linear search. Yeah. The same thing. Yeah. Yeah. All right. So here, for this simple algorithm, yeah, I want to, show you some basic concepts here. Yeah. Let's do analysis. Let's do analysis on the efficiency of this algorithm. Efficiency. Okay? Yeah. So how to represent efficiency? We need to use the number of comparisons used by this algorithm for its efficiency. Yeah. All right. Yeah. So let's do a chart to list all the possibilities. Yeah. Because you may have many possibilities. Yeah. All right. So here I use this chart to cover all the possibilities. All right. The first one, K equals A of 0. In that case, you only need one comparison. The second case, A equals the second element. So you need two comparisons to find it, and so on. Okay? Yeah, the last element, if K equals the last element, you need n comparisons to get a search result. Yeah. But if you couldn't get a match after you complete all the n comparisons, still there is no match, that's the last case. Yeah. No match case, so we put it as the last case. You need n comparisons. So that's all the cases we may have for this algorithm. Yeah. All right. So in all these cases, the first one is the best case. Yeah. Because the number of comparisons used by the first one is the smallest. So we call it the best case. Then the last two cases, yeah, because they need to use n comparisons. That's the largest number of comparison, longer. So we call it the worst case. Yeah. More comparisons you use, the worst of the efficiency you have. Yeah. So we call it the worst case. The best case and the worst case. Yeah. These two concepts. But we also we want to measure the overall efficiency. Because when people talk about the linear search, people also want to know what is the overall efficiency. Yeah. So if we want to find the overall efficiency, you can see it's not good to use the best case, right? Yeah. Because you are too optimistic. Because the most of the time, this linear search does worse than the best case. That means if you use the best case for the overall efficiency, that's not good. Too optimistic. Okay? You cannot do that good. Yeah. Similarly, you cannot use the worst case for the overall efficiency, right? Yeah, because it's worse than most of the other cases. Yeah. So if you still want to use the worst case for the overall efficiency, then you are too pessimistic. Yeah. All right, still not the best description you use. Yeah. All right, so let me see, Elroy, if we use a searching algorithm that looks at the middle of the, good, yeah, middle of the index first, would be the middle index be the best case, then, or would it still be the first index? all right, yeah. So so here, so you want to use the middle, compare key with the middle element, yeah, that way. So actually, so what you are doing here looks like something related to the binary search, right? Binary search, the first comparison we do, we compare the given key with the middle element. Yeah. All right. So here, I mean, related. Yeah. I do not mean the binary search. Yeah. Here, it's not a binary search. Yeah. But if you compare the given element, the middle index would be the best case. Yeah. Yes. Yeah. Correct. Yeah. So it's correct. If you choose middle index element as your first comparison, then the best case would be, the key equals that middle element. When the key equals that middle element, it is the best case. Yeah. Yeah. That's correct. Yeah. All right. Yeah. But here, let's get back to our previous question. We want to find a good measure for the overall efficiency. Yeah, so here, this is the main concept I want to explain for this question. Overall efficiency, this concept here. I want to spend some time explaining this overall efficiency. Okay, all right. Yeah. The measure should include all the cases. Your overall efficiency should cover all the cases. You cannot miss anyone. You cannot miss any case if you want to talk about the overall efficiency. Okay? All the cases must be included in the measure for the overall efficiency. Yeah. So that's the first point. Second, how to know all the cases? Here, in the given chart, we cover all the cases, right? So we have it. So how to know all the cases? Here, we exhaust all the possible cases. Yeah. So we address this point. Next one, another important point, how to combine all the cases. Because you need to combine all the cases in a fair way, in a reasonable way, in a suitable way, to get the measure of the overall efficiency. Yeah. So we need to specify that combination method, how to combine that method. Yeah. All right. Yeah. So for this particular example, we need to make appropriate assumptions. Yeah. Before we can do the suitable combination method, we need to make some appropriate assumptions. Yeah. Yeah. The assumption should be fair, should be reasonable. Yeah. All right. So let's look at the C.2 topic, average efficiency. Yeah. So the measure to address the overall efficiency, we use this concept, average efficiency, to address the overall efficiency. Yeah. All right. Yeah. So let's look at this chart again. Now we want to do certain combination method to get a good measure, fair measure, reasonable, suitable measure. All right? Yeah. So what's the assumptions we want to make? Yeah. Fair assumption we want to make here. Yeah. We assume, first let's look at the first n cases. Yeah. Because in each of the first n cases, we find the key, right? We find the key, given key in the given array. We find it. Yeah. So that's the first n cases. We find it. Yeah. All right. So here we assume that the first n cases have the same probability. Yeah. Yeah. So each element has the equal chance to be equal to the given key k. That means they have the same probability. Okay? Each element has the equal chance to be equal to the given key k. All right? Yeah. All right. But that's for the first n cases. But for the last case, no match case, the last case, what's the probability for the last case? So we need some assumption for the last case, right? Yeah. So here, so let's consider the index case. Yeah, the index, the search function returns a valid index number, so we call the index case. Yeah. Non-negative integer between 0 and n minus 1, that's a valid index. Yeah, so that's the first case. The second, no match case, negative 1. Negative 1 is not a valid index. So that means no match. The given key cannot be found in the given array. So we consider these two cases. Yeah. So our assumption here is the index case has the probability p. Little p is given. Yeah. Little p is a given number, probability p. Yeah. With p between 0 and 1 inclusive. Yeah. Then the negative 1 case, minus p. The complementary part. Okay? 1 minus p. The total probability is 1. Yeah. So the negative 1 case should be 1 minus p. Okay? All right. So then some people may ask how to get the p, right? Yeah. So here we assume little p is known. It's a given value, known value, p. Yeah. the question is, how do you find this little p, probability value, right? Yeah. All right, so here, let me give you the possible answers. One way to get it, we can do statistics based on the history data. Okay? Yeah. So when you apply this linear search algorithm on certain data, yeah, so you should have some history data, right? Yeah. So you just do the statistics on the history data to get this probability p-value. So that's one possibility. Yeah. But there is another possibility. Okay? Yeah. Yeah, because you may not have the suitable history data sometimes. Yeah. Then you just apply the linear search on certain array in the real world situation directly. Yeah, think about that situation you may have. Okay, so you just apply the linear search on a given array. Yeah. In that situation, we can use the dynamic statistics, dynamics on the fly. Yeah, because the elements come in dynamically, in a dynamic way. In the real world, you collect the data, it's a dynamic process. Okay, so yeah, because people collect the data, when you apply the application software, then the data keep coming in. Yeah. So it's a dynamic data. Yeah. So if you have the dynamic data, so you just do the statistics dynamically. Okay? Yeah. 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 So then you use the dynamic statistics to do the prediction. Yeah. Yeah. So you use the history, in this situation, you still use the history data. You use the history data to do the prediction of this probability. Okay? Yeah. So, all right. So here, I just explained how to get this p-value, estimate of the p-value. Yeah. All right. Next, we assume we have the specific p-value, so we just want to see what is the fair way to calculate the average case efficiency. What is the suitable way to combine all the cases? Yeah. All right. Yeah. So here we take two subcases. The first subcase, that's the index case. The second subcase, that's the -1 case, no match case. Yeah. Here, let's consider these two subcases. All right. For the first subcase, what is the average number of comparisons? Yeah. That's easy. Yeah, because we assume they have the equal chance to be equal to the given key. Equal chance. So to calculate the average case efficiency for the first subcase, we just take the average of these n numbers, 1 plus 2 plus ... plus n. So the sum of these n numbers over n cases. Yeah. So the result, after simplification, 1/2 times n plus 1. This is the average number of comparisons for the first subcase. Yeah. The second subcase, we look at the average, but second subcase only has one case, right? Yeah, no match case, only one possibility. Okay, so if you only have one case, its average case is the same as itself. Yeah, that is n comparisons, the second subcase. All right. Now, the last step to find the overall efficiency, the average of all the possible cases here, we want to combine these two subcases in a suitable way. Yeah. This time we need to use the probability numbers. Little p for the first subcase and 1 minus p for the second subcase. Yeah. How do we combine these two subcases with these two probability numbers? Yeah. Here we use the weighted average concept, weighted average approach, weighted average. And their corresponding probability number we treat as the weights. Yeah. The first average case number, 1/2 times n plus 1, its contribution to the weighted average, we need to multiply its corresponding weight p. The contribution from the second average case n, we need to multiply its corresponding efficiency, its corresponding probability number 1 minus p. Yeah. Then we add these two numbers together. That's the way we define the weighted average. This is called a weighted average. We need to, use their corresponding weights for each average case contribution, average efficiency contribution. Yeah. All right. So we get the final formula. This is the final formula. All right, weighted average. That's the way people calculate the average case efficiency. Yeah. All right. Yeah. Okay. So after this step, after we have this formula, another step, in order to prepare ourselves to the next module. So here I do another step. Here we introduce another concept. It's called the dominant term. Because in this expression there are many terms. Okay? All right. The n is a variable. The data size, n is the data size. N is a variable. P is constant. P does not change. P is a constant. Yeah. After P is given, P does not change. Okay? P is constant. Treat it as a constant. Okay? N is a variable. All right? Yeah. So here, if we consider the major term, the dominant term, the major term, yeah. So we only look at the terms containing the variable n. Yeah. So then we have this expression. The parenthesis 1 minus 1/2 p times n. This is the dominant term. Yeah. All right. So here, to show you, why we call this dominant term. So you can actually, you simplify this formula. So here, 1/2 np plus 1/2 p plus 1 minus p n, right? Yeah, so here, because this we treat as constant term. The term containing n, another term containing n. Let's combine these two terms containing n, so we get this term. this term. Here we drop the 1/2 times p constant part, because that's relatively small. So if we drop that part, so we call this major term, this dominant term. Especially when n is very large, so this term dominates all the other terms. So we call it dominant term. This concept will be used in Module 2. Yeah. Here just preparation a little bit. Yeah. All right, so we get this dominant term. So the dominant term gives a good approximation. Yeah. Yeah. Because sometimes our efficiency function could be very complicated. Okay. It may have many terms. Yeah. But we want to use a simplified version of the efficiency function. We just take its dominant term, and we drop all the other minor terms. Yeah. 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 In the next module, I will explain why, if we just take the dominant term and dropping all the minor terms, we can get a good approximation. Yeah. We can get a good approximation. Yeah. So in the next module, I will explain this idea, this view. Okay? Yeah. So we won't throw away too much. Yeah. So we throw away the minor terms, we keep the dominant term, but we will not lose too much. Yeah. So that concept, yeah, that idea, yeah, I will explain in Module 2. Yeah. All right, so today, so we finish C.1 and C.2. The next time, yeah, we have a few more topics left, so we have to complete it in our Monday's class. Yeah. All right, so let's stop right here.